Hello. So I think the sign of a really good problem in maths is that it can really teach you something, right? You get some insight from it you weren't expecting when you started thinking about the problem. And today I want to go from a University of Oxford computer science interview question to a really neat description of something fundamental in algebraic number theory called a quadratic number field, which is basically, if I've got 2 points in a plane, how can I multiply those points to get another point in the plane? And on the way, we'll find a really quite unexpected connection to the golden ratio. So let's start.
Okay, so I won't go through this question in detail exactly, but it was about exploring properties of the following multiplication. So a comma b times c comma d is equal to ac plus bd, comma bc plus ad plus bd. And if you're anything like I was, saw that and thought that has to be completely meaningless. So for example, 1 comma 1 times 1 comma 2 is 1 plus 2 comma 1 plus 2 plus 2, 3 comma 5. And you poke around with this product a bit and you find it's remarkably well behaved. It turns out it doesn't matter which order I multiply the points in. It's also associative, so it doesn't matter if I do 2 points and multiply by a third one, or multiply the last two first and then multiply by the other one. If I define addition of points by doing just coordinate-wise addition, so a comma b plus c comma d is equal to a plus c comma b plus d, then in fact this multiplication distributes. So a comma b times a sum is equal to the sum of the two multiplications. So exactly as we have the real numbers, it all works fine. And there must be a story behind this. There must be a reason for this. And indeed there is. And I want to start this by going right back to how we first think about numbers. So this is maybe a bit ambitious, but we first talk to count, right? 1, 2, 3, 4, 5. And a little later we're introduced to negative numbers and to fractions. And now one nice thing is that at that point we can solve any linear equation. So 3x plus 1 equals 0, x minus 2 equals 5. And then something remarkable happens, and you're told that there are loads and loads of other numbers sort of in the gaps between the rational numbers, irrational numbers, and some of these I can use to solve equations, the square root of 2 and things. They come up from solving equations, and others come up from completely other places like pi or e. They're not to do with solving algebraic equations, at least in the same way. Okay, and I'm proposing for now that we stop at the rationals. Right? We've got enough at that point. We don't want to introduce this massive sea of other stuff. Let's just stop at the rationals. And then let's suppose I want to introduce one new number. So I've got my rational number, and I want to introduce a new number, x. And since I don't really know anything about it yet, I'm not going to put it in the number line anywhere. I'm going to put the number line as the x-axis on a plane and put x at the point 0, 1. So I've got 0, 1, 2, 3, 4. Okay, so this might look a little bit like how we describe the complex numbers. That's not what I'm doing exactly, but it is very closely related. So I want to say that 2x, 3x, any multiple of x by a normal number behaves in exactly the way you expect, and we can scale our value of x to make new numbers. And we can also add numbers involving x to normal numbers, and again I'll get exactly what I expect, so something like 3 plus x will be a number living at this point here. So in this way I can fill out the entire plane that I've drawn here. Now, problems come in now when I have to start thinking about what x times x is, or indeed x times 3 plus x. I've got to work out what x times x is. And I don't really know what x times x is, and I'm sort of free to choose. I'm free to explore whichever possibility I like. But certainly I want this x squared to live somewhere in my plane. So it has to be a normal number plus x. And I'm going to make a choice. So I'm free to make whatever choice I like, but I'm going to set x squared to be equal to 1 plus x. So that is this point right here. We've now got, once I've said what x squared is, a completely fully functioning multiplication of points on the plane. So if I write 2 plus x, so I want 2 plus x multiplied by x, And that's 2x plus x squared, which is going to be 1 plus 3x. So that lives here, 1 plus 3x. So let's go right back to our original question. So if I write a plus bx in the form a comma b, and I write c plus dx as c comma d, and I multiply together those points, a plus bx times c plus dx, then I get ac plus bcx plus adx plus bdx squared. Now, remember what x squared is, it's just 1 plus x. So I'm left with ac plus bd plus, look at everything with an x term in it, bc plus ad plus bdx. Now writing that back out in coordinate form, got ac plus bd, comma, bc plus ad plus bd. And that's exactly the multiplication that I started with. And you'll notice that all I used to define that multiplication was what x squared is. So x squared is equal to 1 plus x. So anytime I have a quadratic, or x squared equaled something linear in x, that defines me a multiplication on the plane. And that's really the sort of take-home thing from this, that a quadratic, x squared equals something, defines a multiplication on the plane. Now let's think a bit more about this particular quadratic, because this is actually a very famous quadratic. X squared minus x minus 1 equals 0 might be even more suggestive, in that one of its roots has a famous name. It's called the golden ratio. So the kind of algebra way of saying what this plane with this multiplication is the rational numbers, assuming my a, b, c, d are all rational numbers, adjoin this new number, this golden ratio. So it's just for numbers together with the golden ratio and how everything multiplies and adds up together. And the very last thing I wanted to mention here is that if you look at powers of x, if I look at x squared, x cubed, well, I know x squared is 1 plus x. And I know x cubed is x times 1 plus x. And so I know that in general x to the n is x to the n minus 1 plus x to the n minus 2. Okay, and that should remind us of something. It's the recursive formula for the Fibonacci sequence. And indeed, if I write powers of x in coordinates, those coordinates track out for me Fibonacci sequence. So we see all wrapped up in this multiplication of the plane, which looked so random to start with, but it's just the golden ratio. It's just the Fibonacci sequence, just wrapped up in maybe an unfamiliar way. In fact, maybe in another video I'll talk about the fact that we can divide numbers in the plane here as well, and that's really what makes this a quadratic number field. Okay. Thank you very much for listening, and I hope you enjoyed. And where did I put that subscribe button again?